Okay, so let's start with the second lecture. Since apparently there were some problems with the tutorial exercises, then I won't ask you any question of the exercise. We can look at them tomorrow.
Not so many tried.
Not so many tried. This is bad news. Okay, so let me start gently. Yes.
Maybe it's not the moment, but you could perhaps give some hint on that exercise of finite structures.
Of course, of course. This is a.
Because this looks like a theorem, no?
This is theorem exercise. It's not that difficult, but I can give you a hint. So the idea, for example, is that the exercise was is this like this? No, this was correct, right? S. I'm forgetting my spelling on the embedding and exercise. This is quite bad. Okay. So the exercise was if L is finite, show that two L structures are elementary equivalent if and only if they are isomorphic, right? And
if and only if there is a single sentence.
Exactly. Actually, there is a single sentence such that if it holds, show that if M is finite, then this is true, right? And this is true. There is actually a single sentence such that if N satisfies this sentence, then this holds. These have to be isomorphic. Let's put it here. Actually, there is.
So there is, for me, it was like three equivalents. There is a single sentence. No.
There's a single sentence phi such that if N satisfies phi, then they have to be isomorphic, right? And this sentence is something like a sentence which is going to depend on this finite M, right? Exactly. So perhaps the key idea is this fact that we can already say how many elements there are in M, right? So we start saying just directly how many elements we have in M. So if the cardinality of this M is, let's say, K, we start by, this formula is going to start by saying there exists x1, x2, up to there exists xk. We say they're all different, right? This big conjunction saying that they're all different, and we say that there are exactly such a number of elements. For every y is going to be equal to one of these xi's, right? And now here, they're going to come a lot of more conjunctions. And basically, this is what we were saying about the multiplication table. So for example, if I have a relation symbol, then I need to say exactly which elements are going to be in the relations and which are not going to be in the relations. So suppose, for example, that your M is here, and I have, this is M, and here I have A1, here I have A2, and here I have my points AK in M, right? And I'm trying to think of these elements as being precisely this x1, x2, up to xk. This is what I'm trying to think of, right? And well, if, for example, R is a relation symbol with arity, let's say 3, just to give you an example, right? Then if A2, A7, and A24 are in the relation, right? If this is happening, then I would like to put here something like R of x2, x7, x24, right? As part of my formula. If, for example, A1, A1, A2 is not in the relation, then I would like to put here the negation of this fact, right? And since there are going to be finitely many possibilities of this.
So you pick an ordering of n?
Exactly. I pick an ordering of m.
And then this orders the variables. And
exactly. This is what I'm going to think about the elements of m as precisely these variables, right? And then I'm going to here list, I'm going to describe completely the structure because I have only finitely many possibilities for every relation, for every function, and for every constant. And I have to list both when a relation holds, both when a relation does not hold, and so on, right? And then
and the images of every function.
And the images of every function, of course. And even the constant saying exactly who the constants are, right? I need to say, if for instance here I have a constant symbol and my constant symbol C is interpreted as A7, right? Then I need to say here C is equal to X7 as part of my formulas, right? And then, well, if you have some structure n satisfying precisely this whole sentence that we're taking here, this is phi, then we know that phi says there are exactly k elements. And well, when if this formula is true in n, this means that by the definition of this relation, this means that I'm going to have elements in n, b1 up to bk that satisfy exactly this formula. And then the function sending AI to BI, where BI is the witnesses that I have for these existential quantifiers, will give me the isomorphism from M to N, right? Because it says precisely this is going to be a bijection because this part over here says that I have exactly K elements. And the fact that this is going to be an isomorphism is precisely that I satisfy exactly the same relations, functions, and constants, right? The constants are exactly interpreted as I wanted. You can think, okay, but basically I solved the exercise. Perhaps this was more than a hint. But sorry, but you can think of this one now. Same holds. Same holds just without this single sentence, but the same holds if L is arbitrary. So it doesn't matter that the language is finite, but the implication has to be like this, okay? Sorry? M finite still, but L arbitrary, okay? And this one over here still holds, okay? You don't need actually that the language is finite. If you have two structures which are elementary equivalent, they satisfy all the same sentences, this is still holds, okay? You can think of it, it's not going to be too different, but still interesting.
You still have the question about the equal sign for part of the language?
Yes. We're doing first order logic with the equal,
So
the equality
the
sign.
language contains the equal
Exactly.
sign, and this is in the relationship.
Exactly. Well, this is not a relation symbol. We take it as a logical symbol. It's part of every possible language. So we're taking as important as any of these, right? So I'm taking. I mean, you can consider it as important as conjunction. It is part of those symbols, and the empty language has no relation symbol, but still the formulas contain this one. Okay.
In practice, it works like a binary relation.
Yes, but if you want, I can make a comment later. It is important to have this symbol outside the relations, because otherwise you can. Well,
in the model, it can mean.
Exactly. I will go to this point a little bit later, either today or tomorrow, because we want equality to be actual equality everywhere. We don't want it to be a relation that satisfies certain axioms that equality satisfies, but we want it to be the real equality. It will be clear what I mean by this tomorrow or at the end of this session. Okay. Okay, right. This is basically because if I treat equality as being part of the relations of a language, we said that nothing is imposing us to interpret this symbol as equality, right? And if I start with a structure in which this is equality, okay, in this structure, this is equality, but we could have different structure where this is not equality. This is just a binary symbol. So we want equality to be just equality everywhere and not just a binary symbol in general, okay? A binary relation. Okay. Now, let me start giving you a definition. And the first part of today's course is going to be about maps that preserve some formulas. So first, this might be an exercise, but perhaps you have already done it before. I'll give you this definition. We say a formula phi is in pre-next form if phi is equal to a bunch of quantifiers. These qi and qn are just either they exist or for all, right? And then there is a formula psi quantifier free, right? So you put on front of the formula all the quantifiers, okay? And the theorem is actually every formula is equivalent to a formula which is in pre-next form. So lemma, every formula phi, well, actually I don't need to specify it, every formula is equivalent to a formula in pre-next form. This is a not very interesting lemma to prove. I won't do it. Let me give you the type of things you need to do. For example, if you have, this kind of things, if you have some negation, for example, and you have a formula here, phi of x, well, you know that you can, this negation, kind of put it inside, and then this becomes for all x. This is equivalent, right? This is equivalent to for all x, the negation of phi of x, and then you're pushing the negation inside the formula. If you have, for example, a for all x phi of x and for every y psi of y, you know that these two can be kind of turned into only one. This is equivalent, this is equivalent to just one for all, right? For all x phi of x and psi of x. And I turn this into just one quantifier and so on. So you can, if you have a disjunction or if you have, well, you need to play with negations and the quantifiers to push these kind of symbols inside the formula. But at the end of the day, you will get a formula which is going to be in pre-next form. Okay? Not too difficult, but a little bit annoying to prove it formally. Okay. Another definition. So we say a formula phi is an existential formula if it is of the form just a bunch of existential quantifiers and then a quantifier-free formula. Right? I should put perhaps, okay, doesn't matter. Yes, let me do it perhaps like this. Here I'm going to put also universal, respectively. Formula. If it is of this form, so I have just a bunch of existential quantifiers, and then some formula x1, xn, and perhaps some other variables y, right? Let's say this formula is of this form, right? And we say it is a universal formula if the same happens, but with universal quantifiers. Oh, this should be another formula, right? Psi. Okay, so existential formula, and let me give you the. So psi here should be a formula which has no quantifiers, so quantifier free with psi x1 up to xn y quantifier free. So those two formulas, existential and universal, are just formulas in pre-next form for which these chain of quantifiers are just all existential or all universal. Okay? Okay, good. Now, this was just some definition about some formulas. Now let me define you what I mean by maps that preserve some formulas. So in general, let M and N be L structures, and phi of x be an L formula. Let H be a map between M and N, right? We say okay. We say H preserves the formula phi of x if for every tuple A in M to the right. I'm writing this because this is the length of this multivariable x, right? So x here could be x1 up to xn, right? And then I'm taking a tuple of length n. If for every tuple A in this power of M, we have that if this structure satisfies phi of A, then the structure N has to satisfy phi of H of A. Okay, so we have a map between two structures, and we would like to say when it preserve a formula, and this happens if and only if whenever the formula is true for a point in M, it has to hold also at its image under H. Okay?
It's just a network.
For the moment, it's just a map. It's not an L embedding. It's just a given map. And the first thing we're going to do is to characterize, for example, L embeddings as precisely some maps that preserve a concrete set of formulas. Okay. This is the first lemma of today with proof. This one was something a little bit easy. So this is a lemma. So let H, well, let M and N be L structures. And H a map between M and N as sets, right? Then H is an L embedding if and only if H preserves all quantifier-free formulas. Oops, quantifier-free L formulas. Okay, so this is another way to characterize L embeddings. Those are precisely those maps which are going to preserve all quantifier-free formulas. And we will see this doesn't look properly right, because here there is only one implication, but for L embedding we were having sometimes two, but this is going to be taken care by negation, because negation is also part of being quantifier-free. Let us prove this result. Okay, so let us prove first this implication. So let us assume that H is an embedding. Suppose H is an L embedding, and we need to prove that it preserves all quantifier-free formulas. How should we start this proof already, if we want to show something for all quantifier-free formulas? What should be the structure of the proof, or the tool that we have to show something for all formulas? Induction on formulas, exactly. This is basically the tool that we have. So we proceed by induction on formulas. Notice that the set of quantifier-free formulas is also inductive. It's just exactly the same definition, just without one last step, which is the one where we added quantifiers to them. But this set is also inductive, right? It also has, the quantifier-free formulas also have just a unique readability theorem. So suppose H is an L embedding, and we proceed by induction on formulas, in this case on quantifier-free formulas. Okay. So we need to start then with atomic formulas. And I guess we need, in this case, one of the lemmas or one of the exercises of the tutorial set about terms. Let me start. So the base step is phi is, let's say, phi of x, right? Is an atomic formula, right? And then, well, we have our three cases. Okay, for these two, this is obvious, right? Because either M always satisfies the truth, and of course N as well, and well, the other one is true by default, right? This is trivial. Now, the other case is we have a relation symbol, right, of arity, let's say N, right? And phi, and sorry, and T terms, T, let's say T1, what I want to say, right, T1x, oh, let me put this RTM, sorry, and I have terms T1x, TMX, L terms, such that phi is the formula RT1 TM, right? This is one possible atomic formula, right? Then we have that, well, M satisfies phi of some A. We have for, let me write it perhaps a little bit clearer, for A in M to the, again, X, let's say, this is going to be some N perhaps. We have that M satisfies this formula phi of A. This is an if and only if, well, M satisfies this formula R T1A TM A. Right? This is just the definition. And this is if and only if, well, this element, right, the interpretation of this term 1 over A Tm over Ma belongs to the interpretation of this relation symbol. But by definition, we said that this is the definition of being an L-embedding, right? L-embedding was preserving precisely the relations here, right? And we said that first, here we're using two things. I'll tell you exactly what we're using here. We're using that, well, I'll write it in a second. This is Tn of h of, oh, let me write it precisely. First, we use now that this is if and only if h of Tm1a h of Tm Ma belongs to the relation in N. This is just because H is an L embedding, right? Just because it is an L embedding, we said that if a relation holds for some elements in M, the image also has to hold in the image, right? In N. And here we use the exercise. The exercise was saying that if I have an L embedding, it commutes with the terms, right? We said this was one of the exercises I put yesterday. We said that this is actually equal to saying this is T of N of H of A, and this is T of N of H of A in Rn. And finally, well, this is exactly equivalent to N satisfying this formula, right? T1 for H of A, Tm of H of A, and this is just N satisfying phi of H of A. Ah, right, I forgot to say here. We show by induction, we proceed by induction on quantifier formulas, but we show something stronger, showing directly the if and only if. So we show that phi of A holds if and only if phi of H of A holds. So we only need to show that it preserves formula. We only need one direction, right? This was the definition, but we're going to show a little bit more in the induction. We're going to show that this happens if and only if, okay? And we will get one direction for free. I mean, as a corollary of this. So this shows the if and only if for the atomic formula R of T1 up to Tm. And we used at some point this exercise. Recall that the exercise said, let me perhaps put it in color. This exercise, what was saying is that H of Tm of a given A has to be equal to Tn applied to H of A, right? This is this commutativity when we have an L embedding of the embedding and the term, the function defined by the term, right? So you can think of it as follows. If you have if this term, for example, was a polynomial, right, in some ring A, and you have an embedding of rings, then what we're saying is that applying H to the coefficients of this polynomial is going to give you now a polynomial applied to the image of these coefficients, if you want. This is one way of instantiating this kind of result, let's say, to the case of polynomials or rings. Yes.
T1 x Tm x delta and such that phi.
Phi is R.
Okay.
Right. Sorry, this is an is. So we're saying phi of x has to be an atomic formula. So if phi of x is one of these two, the result is trivial. Now we're dealing with the case where phi of x is this kind of formula, right? And of course, here I have the x's inside every term, right? Then Right, we show that this holds for an element A, and this is if and only if it holds for the image in N. Right? Okay, this is, we're still lacking one more atomic formula, right? This is the equality, right? So if phi of x is of the form T1x equals T2x, I am writing already like this instead of the strange Polish notation, right? If this is my atomic formula, well then let's prove it, right? Suppose that M satisfies this formula phi of A, and this by definition means that M satisfies that T1 A is equal to T2 of A, right? This is just the definition. I mean, I'm just saying what phi is, right? By definition of the equality, this means this is if and only if the image, right? The image under this function applied to A has to be equal to the image under this function, sorry, 2 applied to A, right? This is, I have just done nothing but interpret what equality means in a structure, right? Okay. Now, well, this direction for sure is easy, right? If I have two elements which are equal in M, well, their image has to be equal, right? T1 MA has to be equal to H of T2 MA, right? Because this is just one element in N. Sorry, this is just one element in M. These two, well, if I apply the same function to both sides, I still have an equality. Why is the contrary? What is the converse also true? Injectivity. We said that L embeddings are injective. So this one we also have by injectivity. See, here we use injectivity. Injectivity of H. Okay. And finally, we use one more time our exercise, right? This we said, we use this here again one more time. This is if and only if T1 of N applied to H of A is equal to T2 of N applied to H of A. And finally, this is the exercise, right? This is exercise. And the last one is simply saying that the formula holds. The formula holds for, so this is if and only if N satisfies this formula, T1 H of A equal to H of A, which was precisely what we wanted to show, right? This is phi of H of A, right? So we're done for atomic formulas, right? Now we need to prove it for conjunctions and negations. This is easier. So here we use really everything about being an embedding, right? We used the injectivity here of the embedding. Here we used this fact about the relation of the embedding. And concerning the functions, this is kind of hidden in this exercise that you need to do. But the part about the functions, I mean, the condition of an L embedding to kind of, I state this condition as a commutative diagram for the functions of the language. Basically, you need to use this to prove this kind of commutativity for all terms. And this is what we used also in both cases. We really used all conditions of being an L embedding. Okay, now the inductive step. So we suppose the result holds for, let's say, psi1 and psi2, right? Now we have two cases. If phi is the negation of psi1, right? Let's say phi of x is the negation of psi1 of x, right? I can put here the x's already. Then, well, this is just the inductive step, right? Because let me perhaps put it here. This is just the fact here for negation. We're using that our induction hypothesis was a little bit stronger. So we have that M satisfies phi of A. This is if and only if by definition, right? This is the negation of psi1 of A. But this by definition is that M, by definition of the negation, right? This is just that M does not satisfy psi1 of A. And by induction hypothesis, this is it does not, N does not satisfy psi1 of H of A. This is the induction hypothesis. And of course, this is the same as N satisfies the negation of H of A. Okay? So here is just basic induction hypothesis. And here's the fact, I mean, this is the point where we really need it in the induction hypothesis that we're proving the if and only if. I mean, this is basically why we chose a stronger induction hypothesis, so that we can deal with this case easily. So this is one case, and the other one is if phi is psi1 conjunction with psi2. Well, then this is also super easy, right? We have phi of A if and only if M satisfies psi of A1 and psi 2 of A, sorry. And this by definition, we know this is M satisfies each one, right? And M satisfies psi 2 of A. And here we use the induction hypothesis to claim the same thing for H of A. Okay. This is not very complicated, and here we use again just the definition of the conjunction. Phi of H of A. Okay, this finishes one direction, right? This was not complicated at all. We satisfy a conjunction if and only if we satisfy each of them. But for each of them, we have already the result. So this is if and only if we satisfy in N the same thing, but for the image. And if we satisfy this, is the same as satisfying the conjunction, which is this formula, right? Okay, and those are all quantifier-free formulas. We already did all quantifier-free formulas, so we already have one direction. So now let's prove the other direction. Now we have a map which preserves all quantifier-free formulas, and we need to show it is an L embedding. So we need to show H is injective first. Now this direction of the proof. So let us first show H is injective. So for injectivity, consider, well, let me ask you, what should we do to prove injectivity, perhaps? So we're assuming this map preserves all quantifier-free formulas. Whatever quantifier-free formula you give me, it will preserve it. So how should we prove this map H is injective? Yes, but which formula? If I take just equality, it won't work.
A doesn't equal B.
Exactly, but with variables, but yes. So consider the formula phi of with two variables, right? X1, X2. This is the formula, just X1 different from X2, right? Then since we have that, if M, or well, given, let's say, given now A and B in M, right, with A different than B, we have that M satisfies then this formula phi of AB, right? Because precisely they're different. But then this means that N has to satisfy this formula for H of A and H of B, which means that H of A is different than H of B. And this shows injectivity because we preserve this form, right? It's nothing difficult, but just to show exactly which formula we need to use to show that H is injective, right? Okay. Now, let us show that given a relation symbol of arity, let's say R, or let's say N, then we need to show that if H is an embedding, we need to show that this relation holds for some tuple in M, if and only if the same relation holds for the image in N, right? So which formula shall we take as in this case to prove this? Right, we want to show, let me say it like this, we want to show if this is an L embedding, it has to preserve the relations, right? We want to show that, let me put it like this, that if A for every A in M to the N, we want to show that if this is in the relation, then this is an if and only if H of A is in the relation of N. This is what we want to show. So what formula shall we use? Any guess?
A1 to AN.
Right, perhaps not A1 to AN, but because those are
Oh, well, yes, it is. Okay.
R of X1 up to Xn, this is going to be the formula, and then it is going to preserve this one, right? So consider exactly. Consider phi of X1 up to Xn given by, this is just an atomic formula, given by R X1 Xn, right? This is quantifier free, and of course, now we have, well, let's do this completely until the end, right? So this will give us just one direction. Notice that here we need an if and only if, right? This will give us, consider this formula given by this, then we have that for A in M to the N, if M satisfies, well, let us put it like this. If A belongs to this relation, right? This one is if and only if M satisfies this formula, right? Or let me put it like this, A1 up to AN, right? Which is exactly saying that M satisfies this formula phi of A. Okay. Right, okay, let me delete this, but well, okay, it doesn't matter. Perhaps I can do it like this. This, because preservation of formulas only goes one way, this implies, of course, that N satisfies also R of H of A1 up to H of AN. And this is what we wanted, right? We know that this is if and only if H of A belongs to its interpretation, but I have only one direction. So how can I get back? Exactly. So we consider this one for going this way, and we consider this one for going the other way around, right? Because if I am not in the relation, then here I satisfy the negation, here the negation, and here also the negation, which is the same as going back. So I need to consider both this formula and its negation such that this is This is correct. Good. Now, finally, we also need to take care of the function symbols, right? For being an L embedding, we say we need to preserve all relations, but we also need to have this commutative diagram. So if, let's say, G is a function symbol, right? Such that, let's say, its arity is also n, right? So this means my function, the interpretation of this function symbol gives me a function from mn to m, right? We need to show this commutative diagram, meaning that h of g of a, and here is my function, is equal to the interpretation in n of h of a. This is what we need to show, right? So which formula shall we use to prove this? We need to show this. Any guess? Yes?
Like the function with n variables equals xn plus 1.
Exactly. That's perfect. So consider the formula phi of x1, xn. Let me put a different variable here, y, or just this is correct, right? And let's write x. This is just x1 up to xn, right? Consider the formula phi, given by g of x equals y. Right? This is a given formula. Then, of course, we have that m satisfies for, well, let me put it like this, for a in mx and b in m, we have that m satisfies this formula ab, right? If and only if, well, f of a equals b, right? But since it preserves formula, we have that this is equivalent to n satisfying phi of h of a, h of b, right? Which is equivalent here to saying h of, well, let me put it like, in this case, this is going to be equivalent just to say, sorry, this f was a g. So this is equivalent to say g to the n of h of a equals h of b, right? But from this part, let me put the if and only if here. This one here, this is also equivalent to say h of g of a equals h of b, right? So if these two are equal, this means that this one here is equal to this one here, which is what we wanted. But here we're lacking still one missing direction, right? So we also need to consider perhaps this formula and its negation again. So we need to consider both formulas. So that here we have an if and only if, right? And in this case, we do have that this is holding if and only if this is holding. And since these two are equal, then we do get what we wanted. Yes? Shall I say it again? So we start assuming that m satisfies this formula. And since this formula is this one, right? We have that the image of a under the interpretation of this function has to be b. And if this holds, well, if I apply h to both sides, I just have this. This is from one side. This is just nothing complicated. I used here in this if and only if that h was injective, but we already showed this was the case, right? Okay, this is on the one side. On the other side here, I use preservation of this formula to get this, and I use preservation of the negation to get an if and only if between these two formulas, okay? This is where I use the negation because one implication gives me just the preservation of this formula, and if this is not the case, then this is the same as satisfying the negation, and then I preserve the negation, and I get the if and only if, okay? Is this clear? Or shall I write it down more precisely? Yes.
Just to recall the definition of L,
L embedding, yes.
everything is if and only if, right? Like relation, I mean.
That's correct.
The original definition is like the relations, like the relation holds
In M, if and only if, yes, that's correct.
Function.
And the function, well, this is not an only if and only if, but an equality. It's like a commutative diagram, right? Let me write it down. Doesn't matter because it's better if this is clear completely. Right. So right. This is the definition of the embedding. So for functions, right? I mean the condition of being an L embedding. These were kind of four conditions: to be injective, to preserve relations. This was an if and only if, right? And for function symbols, this is if G, it says something like this. If G is a function symbol of my language, of arity N, then the following diagram commutes. And the diagram is the following. I have here M to the N, and here I have this function, which is the interpretation of my function, right? Of my function symbol. This is how I interpret this symbol in my structure M. It gives me a function, right? I have exactly the same thing here for N. This is just because these two are structures, and in every structure I need to interpret every symbol, in particular this function symbol, right? Between this and this I have my map H. And between this and this I have the map H just coordinate by coordinate, which is the one I put it like this, just H times H. And what I'm saying is that this diagram has to commute. So if I apply first my function to a tuple A, and then I apply H, it has to be the same as applying H to each coordinate, and then apply G, which is exactly what this is saying. This is just exactly the same as the commutativity of this diagram, okay? And this is what we're showing here. So we started with this formula, right? This is just the satisfaction relation, the definition of the satisfaction relation. And here, the if and only if just goes in this direction, and I applied H, and injectivity gives me an if and only if, right? On this side, one direction from here to here is just that I preserve this formula, and the other direction is that I preserve its negation. And the last step here is just the definition of the formula. If this formula is this one, then I must have that these two are equal. And the final step is just, since in this hand side and in this hand side, I have both an equality with H and B, well, they must be equal between them. And this is precisely what we wanted to show. Okay?
Sorry, but why are you considering the second formula G not equal Y? Because I would say that, like, we take A, we check that that formula up there, then we define B as the image of A by G, and then we apply just the procedure to the first formula, we get the result. No?
Right, but
all AP.
But it's not all AP, it's only A.
yes, but how do you go? How do you go?
I mean,
Oh, you're.
it's all AP.
I mean, you want to prove.
For every A, that formula up there. Then B is not, you can P is not free, P is just the image of.
Perhaps you're right. Give me a second. So you're saying, right? Perhaps you're right. Perhaps I don't need the negation, right? Because what you're saying is, okay, if let me write it here. Perhaps you're right.
No, you need negation to come back, otherwise you get a new solution.
No, no.
Phi h of a is
He's-
equal to new b element and
Yeah, he's saying the following. If I understand, well, you can explain it, but you take a in m to the x, right, such that g of m of a equals b. This is his starting, right? So this means that, I mean, this is an if and only if m, well, let me put it like this. This implies just that m satisfies this formula phi of ab. And this implies that n satisfies then this formula phi of h a hb. And this indeed implies that the last one, right, that g n of ha equals hb, right? And here we're using that this is equivalent to h of gma equal h of b. So supposing this, we can conclude from these two that these two are equal, right? Yes. So you're right. I mean, if I want to put here ifs and only ifs, I do need negation, but just to show this, I don't need it. You're totally right. It's a good point. Okay. Good. So this was a long proof just to show that L embeddings can be characterized as precisely those maps that preserve quantifier-free formulas. Yes.
Do we also need to show, I mean, do we need a formula that
Oh.
shows that constants?
Absolutely.
The same.
Absolutely. I was finishing the proof a little bit earlier. Let me delete the condition of being an L embedding for functions. Yes, we're lacking one formula. Sorry, because the condition for constants is that the following. Well, it remains to show that for a given constant symbol, right, h of c of m equals c of n, right? This was the last condition of being an L embedding. It has a condition for the relations, for the functions, and for the constants, and being injective. And we're still lacking this one. Any guess for the formula we're going to take? Yes. Take phi of x and the formula to be the formula to be c equals x, right? And then in this case, if well, we have m satisfies c equals x, let's say applied to a, right? This is if and only if c of m equals a, right? This one preserves the formula, so this means n satisfies also that c equals x, but applied to h of a, which is if and only if c of n equals h of a. But from here we know that this is an if and only if h of c of m equals h of a. And then again, from these two, we can conclude that h of c of m is equal to c of n. Okay, it's basically the same argument for what we have already done, but with the c. Okay, now the proof is really finished, and you just show that L embeddings are precisely those maps that preserve quantifier-free formulas, right? So this directly suggests that there could be maps which are kind of stronger than L embeddings, right? Which kind of map would you guess should be a little bit stronger than an L embedding. Exactly. Just a map that now does not preserve only quantifier-free formulas, but all formulas. And now these are the kind of maps we're going to be interested in. So this is an embedding which is really, really strong. And we're going to call this embedding, well, it's not a great word. It's called elementary embedding. It has nothing of elementary. It's stronger than embedding, but this is the name they gave it. They being, I don't know, the fathers of model theory, something like this.
Would the image mean the image of that map be very different?
This is going to happen, of course, of course.
Maybe that's what I mean, I guess, or-
Well,
I know something like that.
I agree, but why the name elementary also for elementary equivalent? I have no idea why. Yes, so definition. A map H between two L structures is an elementary L embedding if it preserves all formulas. Okay, and the observation, perhaps this is worth saying, equivalently, H is an elementary embedding, L embedding, if for every formula, L formula, phi of x, and every A, an element of the right Cartesian power of M, we have that M satisfies phi of A if and only if N satisfies phi of H of A, right? So the only observation I'm doing here is that you will find in books perhaps this definition from elementary embedding. The one I gave you here, it says H preserves, which is usually just, I define it as just one direction, right? But since we have negation along all the formulas, this will keep us by free and if and only if, right? So this definition is only giving you this direction, but since we have negation, this is going to be an if and only if at the end of the day, okay? They're equivalent. Of course, this seems stronger, but in the presence of negation, we have always this if and only if, okay? So all formulas go up and down. Perhaps I should have said this before. This is also an observation. So recall that our notion of substructure means that the inclusion is an embedding. This is perhaps a good observation too. Suppose that M is a substructure of N, right? Then we have that, first of all, if phi of x is quantifier free, then for a tuple M in Mx, we have that M satisfies phi of A if and only if N satisfies phi of A. This is just what we just proved, but in the case our map H is just the inclusion, right? The identity, because if it is quantifier free, we just show that this was an if and only if, right? But it also holds, for example, that if, I mean, this is quite easy to see, but if phi of x is existential, is this with C or T? T, you sure? Okay. If it is existential, then existential formulas go up. So if this formula is satisfied for some A, then of course it's also going to be satisfied for N. They might not go down, right? You can think of this as fields again. I might have in the bigger structure a solution for a polynomial which is not a solution here, but they always go up. If I have a solution for something here, well, the same witness is going to be a witness for a solution in the bigger structure. Right? So existential formulas go up, and the same way universal formulas go down. Right? So if X is a universal formula, then here I put the arrow this way, right? Universal formulas go down. And well, what we're saying here now is that in the case, let me put a definition. When the inclusion now is an elementary L embedding, not just an L embedding, then we call this an elementary substructure, and we use a certain notation for this. So definition, when the inclusion, well, let me put it like this. Okay, when the inclusion between, let's say, M and N is an elementary embedding, we write this with this symbol. So we put this kind of curly relation symbol between both. This is just to express that I'm not only a substructure, but I am an elementary substructure, or just saying that the inclusion is an elementary embedding. We write it like this and say M is an elementary substructure. Of N. Okay. Now, notice that this is a pretty strong condition between two structures. Let me give you some examples of this. So, observation. Yes. A universal formula is a formula which has just a bunch of universal quantifiers and then a quantifier-free formula. So it has only universal quantifiers in front of a quantifier-free formula. Okay. So if it has only universals, then this is just a bunch of for alls here, and this is going to be also true here. Shall we prove this, or this is kind of clear? In this case, for example, the idea is that if this is existential, then you're going to have a witness in M. And because this witness, I mean, the remaining of the formula is quantifier free, we use part 1 to bring it to N, right? Shall I write it? Anyone wants me to write this down? I can. I mean, we have time. Is this clear? Okay. And the for all is the same, right? If it is happening, if something is already holding for every element in N, for sure it's going to hold for every element in the substructure. Okay. We can do this later in a pause if you're puzzled by this. It's no problem. Now, note this, for example. Just one example of how strong this is. Let's take, for example, a field F such that F is an elementary substructure of the complex numbers in the language of rings. Then F, for example, has to be already algebraically closed. Okay, so this is really much more stronger than just being a substructure. Being a substructure, even here, only means even not being a field. Being a substructure in the language of rings is just being actually an integral domain at most, but not even a field, right? Because we don't include in the language of rings the inverse for multiplication. We only added the inverse for addition. But in this case, this is not only a field, but even a field which is going to be algebraically closed. So this is quite strong. Shall we understand why this is the case?
So can you repeat?
Yes. What I just said is that the relation in the language of rings. Well, let me put this not in this observation because we're going to get confused, but in the language of rings, recall, for example, what I said first about groups, right? When we were thinking about groups in the language, in this language, which was times minus 1 and 1, right? We said that the substructures were really subgroups. But if I restrict my language just to this one, we were saying the substructures are going to be only monoids, right? Because I don't have this minus 1, right? So I don't enforce a substructure to be closed under inverses. The same is going to happen for the language of L rings and a given field. If I have a field in the language of rings, the substructure might not be closed under inverses for multiplication. So what I get is only, I will still get an integral domain. So I cannot have divisor by 0 because this is a universal formula. And universal formulas, we said they go down, right? I can say, notice that, let's write it down. In the language of rings, suppose we have a field K, which is an L ring structure, right? Then if, let's say F is a substructure of K, right? Then F might not be a field, right? Because as we said, we don't know if it is closed under multiplicative inverses, but however, it's going to be an integral domain. We cannot have two elements which are not 0, which multiplied get me the 0, because since F.
But this is just because you will prove that it's a subring, right? Because substructure of an actual ring, I mean, this ring is subring. Right?
Exactly. This is going to be a subring of.
Not really about formulas, right? It's just about being subring.
I agree. This is going to be a subring of this one, but it is a subring of this one because precisely because we are in the language of rings. Yes, I agree. And
But being a ring means it satisfies the sentences that the ring.
not all the sentences, but the quantifier-free sentences, yes, right? Or the universal formulas, but not all the sentences. This we don't know, right? If it satisfied all the sentences, then it will be actually algebraically closed, because this we can say in a sentence. Well, not in one sentence, but in a bunch of sentences, right? That's correct. But in general, I don't have a field. In this case, if I truly have, for example, this relation, then I'm going to have not only a field, but in this case, since this is algebraically closed, this is also going to be algebraically closed. Yes?
So there you say take a field, but you don't take field. Just have to take F.
That's correct. Take a ring even, right?
Yes, take F an elementary substructure.
Exactly. Take an elementary structure. I agree. Take F such that this is the case. I agree. Totally right. If this is an elementary substructure, then this has to be a field and it has to be algebraically closed. Correct. Shall we shall we do this proof? Or perhaps let me skip this proof to later, because we're going to see actually that we can say with less than this relation that, I mean, we don't even need this. Let me do this remark also here, perhaps. This is an important remark. This is the one you were saying. Remark is that if I have an elementary substructure of another, then in particular, this is stronger, but in particular, they have to be elementarily equivalent, right? So recall this relation is for formulas, and formulas might have free variables, right? Here, I'm saying that if a formula holds at a given point, it also must have been true for that point here, right? This was just for sentences. Sentences don't have free variables. What I'm saying is that this is in particular, I mean, if the formulas with free variables move, for sure, a sentence that does not have free variable also is true in one and the other at the same time. And this is just an instance of being elementarily equivalent. So recall, this is perhaps quite important to have in mind. This is sentences, so no free variables. And this is formulas. This is stronger. Okay, this is much stronger. It says that I can move formulas with elements from M up and down, right? This is a bit stronger than this one. Okay. Yes.
And is it possible to have an elementary embed? I mean, to have a substructure which is elementarily equivalent, but for which there's no elementary embedding. Like all the sentences are satisfy the same sentences. It's a substructure, but there is embedding which preserves all formulas.
Absolutely. This can happen. This can happen. So we can have even two structures which satisfy the same sentences. One is a substructure of the other, but this relation won't hold. I'll give you an example of this later. Yeah, this can happen. This can happen. For example, yes, I think something like this. Something like this. You can have the language is here just one function symbol. Of arity 1. And I take the following structure. I take n, and the interpretation of this structure is the successor, right? And now I take, oh, wait a second, I take, no, I don't want to take the successor. I want to take, give me 1 second. I want to take, perhaps this one, sorry. I want to take plus, and the arity is 2. And I want to take just z with plus, right? I have a substructure which is this one. I take just the even numbers, right? This is a substructure because it's still closed under sum, and it is the same sum, and well, you can check that the inclusion preserves this symbol, right? And actually, you can prove these two structures are actually isomorphic, right? Because the map sending x2 to x is going to give you an isomorphism between these two, right? Since they are isomorphic, they're going to satisfy the same sentences, right?
But what about
So they're isomorphic, but this relation does not hold.
But are they really isomorphic? Because you could say for every, like in the big one, for every,
Let- let-
in the smaller one, for every x, there exists a y such that y plus y equals x doesn't hold in the bigger one. Right?
I think it does, right? Well, let's check that this is an isomorphism, and if it is an isomorphism, let's
Right, okay.
Right, I mean,
My sentence doesn't hold in either one. Okay.
right, okay. But at any rate, if there is an isomorphism, actually by this you need to do this exercise in the exercise set. If there is an isomorphism, these two structures need to satisfy the same sentences, for sure. And we can show that the map. I mean, let us show. This is a good exercise. Let us show the map H going from Z to 2Z. Of course, the map just sending X to 2X is an isomorphism, right? It is clearly bijective, right? It is bijective. Bijective. Okay, so we only need to show it is an L embedding, right? So the conditions from L embedding. So we only need to show that this diagram commutes for the function, right? We need to show that H of X plus Y is equal to H of X plus H plus Y, right? This is the commutativity of this diagram, but this is kind of silly to show, right? This is, of course, this one, right? So this is indeed an isomorphism. This shows that these two structures, so this implies that these two structures, Z plus is isomorphic to 2Z, sorry, is elementarily equivalent to this one. However, let us show that this is not an elementary substructure. I mean, they can be isomorphic via some map, but the inclusion, I mean, this is for sure not the inclusion, right? This is just some isomorphism, which is different, which grants us this, but the inclusion is not an elementary map, right? And this is because, for example, we can say there exists, what shall we say, that does hold in one and does not hold in the other one. With parameters with from 2Z, right? Okay, let me make it easier for us. I'll make it easier. Let us put here an order, right? Let me put an order, and let me show that this function also preserves the order in both, right? So that we still have what we need. Otherwise, so we need to preserve that. We need to, okay, it is bijective. It preserves the function symbol of my language. I need to show it preserves the relation, right? So I need to show that if X is smaller than Y, then this holds if and only if 2X is smaller than 2Y. But this, you know, it holds, right? Okay, so these two structures, even with the order, they're isomorphic. One is a substructure of the other. And now I can say this formula, right? Consider, for example, the formula Z with plus and with the order satisfies, actually the plus, I don't need it even for anything, satisfies this formula. There exists some Y such that Y is in between 0 and 2, right? Right? This is a formula of the form phi of 0, 2. 0, 2, of course, are not elements in my language, but I'm applying this formula to two elements in this one, right? If these two structures were, if the inclusion was an elementary embedding, this formula needs to be true also in the smaller one, right? But this does not hold in the smaller one because there is no one in the smaller one between 0 and 2. Right? Let me write this down properly. Actually, I should have taken away the plus. The plus, I didn't use the plus everywhere. Ah, that was a good idea. Sorry. I agree. There were plenty of examples at the end of the day. So, right, if these two structures, I'll say if this was the case, right? Oh, this is 2z and this is z. If this holds, then this formula phi of, this is phi of, let's say, y1, y2 equal to the formula there exists sub x, x1, x2, right? Which says there exists a y such that x1 is smaller than y, smaller than x2, right? Since this formula holds for, I can take any two elements in the smaller one, right? I mean, if this is true, then we have that, let us call this structure n and this one n. Then we have that m satisfies this formula phi of 0, 2, if and only if n satisfies this formula phi of 0, 2, because these two elements belong to this one, and we're saying the inclusion is an elementary embedding. It satisfies any formula, in particular this one. So this is true here, of course, because we have that 0 is smaller than 1, smaller than 2, but of course this is not true here because there is no element between 0 and 2, right? So this cannot happen, okay? This is an example of even two structures which are isomorphic, but for which the inclusion is not an elementary embedding. Yes?
I guess we should also consider, I mean, it's an obvious extension, but like you can do any embedding you choose.
Yes.
You just construct a different sentence which says like a bigger number of elements in between.
Right.
Like, I mean, you can always, no matter what the embedding, like you just say there doesn't exist, there exists like a million different elements in between x and 1. You know what I mean? Like,
I think I do, but
no, because I mean, we could have chosen x goes to like
here
million x, you know. And,
yes, I agree.
and in that case, we would need to adjust
the formula.
the formula.
Yeah, I agree. I agree. I mean, but we might need to change this structure here as well. You're saying I could take here not just multiples of 2, but multiples of whatever. This is what you're saying, or?
Oh no, I just thought that you could, like, for your embedding.
Yes. Well, I took this. I mean, this part was only to show that these two structures
Okay.
were isomorphic, right?
Okay.
And
so are we obligated to take the actual inclusion?
well, if for right, you're right. I'm only saying that these two structures are not, one is not an elementary substructure of the other, right? I'm not saying that there is no.
But if we wanted to say there is no.
This, of course, this is something different. But actually, this one is already an elementary embedding. Actually, any isomorphism is an elementary embedding, right? Perhaps let me write this observation as well. Note that observation. Every isomorphism, let's say L isomorphism, is an elementary L embedding. So we do have that this is an elementary embedding between these two structures. What we're saying here is that just the fact that there is an elementary embedding, it doesn't imply that the inclusion has to be an elementary embedding. Okay. Good. Okay. Yes.
So it's from the thing before in the class. You said,
For the thing about algebraically closed and
so you said K is a field, not L structure.
yes.
But I think you should actually say that K is a ring with its usual L structure. Because it would be a field with another L structure.
Of course. I mean, when I say that this is, we're treating it as an L-ring structure, is that we're interpreting the symbols here precisely as the operations in K, right?
K is a field with its usual.
Yes, I agree. I agree. Which, I mean, with it's canonical, right? L-ring structure. I agree. If I say, for the rest, if I say a K in the L-ring structure, it would always be the canonical. Otherwise, I will state it differently. But you're right. It's good to bear in mind that, of course, the symbols here can be interpreted as we want. Of course, when I'm seeing a field as an L-ring structure, I mean with the canonical interpretation. That's correct. Let me postpone a little bit this fact about the algebraically closed fields because something a little bit stronger it holds as well. Let me say it, and we will prove this later. Observation is that if, let's say, like this, already if a field is elementarily equivalent to C, then F is algebraically closed. Okay, this holds already with a weaker, under a weaker condition. Okay, so this is basically saying that we can express being algebraically closed with some sentences in the language of rings. And of course, then if we have that F is an elementary substructure, then in particular they satisfy all the same sentences, then this is going to happen. And I'll show you this part. Perhaps we can do it today at some point. Okay?
Yeah.
I will do it, but let me. This is easy, right? Exactly. We're going to say there are solutions, right? I mean, we just need to quantify over all the possible. I mean, the only possible problem is that here we need to quantify. I mean, we need to say something about all possible polynomials, and we said that polynomials, we don't have coefficients for F, right? Okay, let's do it. Let's do it. Okay. So consider this is okay. So, well, first we need to ensure that we add in a sentence saying that something is a field, right? This is easy. Those are the field actions that you have seen in any course of abstract algebra. So there is this formula, let me call phi field, right? This is a formula saying, for example, that for every x, for every y, and for every z, your operation of plus is associative. Oops. Right? You need to give also another one to say that it is commutative because we're working with commutative fields. You need also to say, and this is a list of finitely many axioms saying that you're a field, right? Just the usual field axioms. Shall I just skip and not write them all? Just the field axioms, okay? And there are finitely many, I assure you. This is just saying that there are inverses for addition, saying that 0 times an element is always 0, saying that 1 is neutral with respect to multiplication if you're not the 0 element, and the distributivity loss, right? And those are all just finitely many axioms that fit into one single big formula, right? Sentence even, right? Okay, this is just one sentence for being a field. Let me save some space and put it like this. Now consider the following formula for, let's say, for d bigger or equal than 1, right? I'm going to have a formula saying that any polynomial of degree d, which is monic, is going to have a solution. And I only need monic polynomials because if I have a polynomial which is not monic, I can divide by this coefficient, and the first has a 0 if and only if the monic polynomial has a 0. So consider this one. So I said for every y1 up to for every y d minus 1, there has to be an x such that x to the d plus y d minus 1, x to the d minus 1 plus up to, oh, I need actually, let me start with 0 here. X to the y1 plus y0 equals 0. Right? Let me write this formula as the formula psi d. This is actually a sentence, right? It has no free variables, right? And of course, this has to hold in any algebraically closed field because it says take any polynomial which is monic in of degree d, then you must have a 0, right? And this cannot be the 0 polynomial because, well, I have here a non-zero polynomial, right? Because I took it to be monic. Then, since C, for example, satisfies, of course, being a field, and C satisfies also this formula psi d for every d, then if F is elementarily equivalent to C, F also satisfies these sentences, right? Then F also satisfies being a field, and it has to be also algebraically closed, right? Because it satisfies this for every b bigger than 1, right? So now if you give me a polynomial, so if, let's say, if P is a polynomial here, right? Let's say P is equal to, let's do it properly. A d x to the d is 0, right? I have this polynomial with coefficients in P, then different than the 0 polynomial. I mean, with, let me put it like this, with AD different than 0, right? So that we know this is not the 0 polynomial. So I need to show that this polynomial has a 0 in F, but this is already taken care by my formula psi of d, right? P has a 0 if and only if this polynomial P divided by A, which is just x to the d, a d minus 1 divided by ad, sorry, ad, x d minus 1, and so on up to this one has a 0, right? Because I'm just divided by A. If this has a 0, of course, this has a 0. And if this has a 0, this must have a 0, right? Now, since F satisfies this formula psi of D, right? We have that F satisfies this formula, right? In particular, I can take, since this holds for every y0 up to yd minus 1, I can take y0, yd minus 1 to be precisely these coefficients, right? Taking y0 to be a0 divided by ad, and yd minus 1 to be ad minus 1 divided by ad, we have that F satisfies precisely this formula. There exists an x such that x to the d plus, well, let me write it like this. This is just such that p of x divided by a to the d is equal to 0. And of course, having an x which satisfies this, it is precisely having a 0 for this polynomial. So this field must be algebraically closed. Okay? Good. So let me just check what I wanted to. Right. We have 10 minutes. Let me now give you an easy criterion to know when is the inclusion and elementary embedding, right? For the time being, we only know that this has to hold for every formula. There is one way, a shortcut to know that a given inclusion is an elementary embedding. This is called as the Tarski test lemma. This is called Tarski's test. Let me write it in the way I want. Right. This is, it says a little bit more. It's an interesting one. So let N be an L structure. And take A to be a subset of N. Okay, for the moment, this is just one subset. Okay, I need to introduce you. Okay, no, I don't think we need. Okay. Okay. So suppose for every L formula, phi of x y with x just one variable and y just any y1 up to yn. This is a multivariable, and every tuple A in A to the n. Suppose it holds the following. It holds that if n satisfies this existential formula, so n satisfies that there exists an x such that this formula holds for A in A, then I can find a witness already for this formula in A. Then let me put it like this. It implies that there is B in A such that n already satisfies phi of B A. Okay. So we're assuming I have a subset of my structure, and I'm assuming for every formula with just here one variable, if n thinks that there exists an element which satisfies this formula for a tuple A, then I can already witness the formula in A. Okay. So this thing, it only says that there is an element in N which satisfies the formula, but here we're saying a little bit more. We need, it does satisfy that the witness can be chosen in A. Okay. If this whole thing holds, then first of all, let me put it like this: one, A is the universe of a substructure of N, and two, actually, we have that A is an elementary substructure of N. Okay, this is enough. So notice that here I start with any subset, and the first part of the claim says that already this has to be a substructure, and moreover, it has to be an elementary one. Okay, so basically we're saying it suffices to show that whenever I have an existential formula satisfied in N, I can find witnesses already in my substructure if you want. Okay. Shall we do this proof now or do the break first? This is like a perhaps 10 minutes proof. It's not too difficult. Let's do it perhaps and we finish this part. So there is at least one thing that we need to prove in order for this to be a substructure, right? It's a silly thing, but we need to show it because we need to show any substructure has to be at least what? The very first thing we defined for L structures. Any L structure was having a universe, but this universe must be non-empty. So we need to show A is non-empty at least, because otherwise this is for sure not a substructure. Every structure is non-empty, so we need to show A is non-empty. But this is kind of silly. So proof. First, notice that A is non-empty since N satisfies this formula, right? N satisfies this formula, and if this formula is satisfied, it must be satisfied by a witness in A, right? And this implies, perhaps we can put here our condition. This is condition star. So this implies by star that there is B in A such that B equals B, but the important part is, of course, this one, right? That there is at least an element in A, so A is non-empty. Okay. So now if we want to show that this is really the universe of a substructure, we need to show that, well, it has to be closed under the function symbols of my language, right? I mean, if I have a substructure, it better define a proper, for every function symbol, we need to have an actual interpretation in this substructure, right? And well, we need to be sure that then this set A is closed under all function symbols of my language, right? This is perhaps the first part. Then if, let's say, G is a function symbol of my language, right? Of arity, let's say N, right? Then, of course, N satisfies, N for a given tuple in A to the N, of course, N satisfies this formula. There exists there exists X such that, well, G of A equals X, right? This is a triviality, but it does. Then by star, there is a B in A such that N satisfies that G of A equals B. Hence, A is closed under the function, sorry, I put right, G of N, right? So I have an interpretation for my function in A, right? Okay. So this already shows it is a relation because, of course, we define, I mean, what is the obvious interpretation for the relations in A is just the intersection with A of the relations in N. This is just a subset. So for the relations, we have no, I mean, we're obliged to take just the restriction of the relation to A. And for functions, we needed to show that they are closed under functions, but of course, this is the case. Also for, right, for constants, right? If C is a constant symbol, I need to show it is in A as well, its interpretation, but this is again a formula. If C is a constant of my language, then since n satisfies there exists an x such that x equals C, then this implies that the interpretation has to be in A, since by star there is some B in A such that C of M equals B, right? So the constant symbols are also part of A. Okay, so now we do have a substructure. We now need to show that all the formulas are preserved, right? So we need to show this second part. So this first part grants part 1, and we need to show now part 2. And part 2, we do it by induction on formulas. Okay. So for 2, we proceed.
We didn't do the relations, but this is obvious.
Exactly. So I didn't do the relations, but if I want it to be a substructure, I'm obliged to interpret the substructure, the relations as just the relation intersected the right Cartesian power of A. And with this definition, of course, I'm going to have an if and only if, right? Because this is the way I define the relations on A, right? And this is the obvious interpretation of the relations such that I'm going to have a substructure. So in this case, I just put them like this, and I have no chance to fail, right? But for the functions, I cannot take, if I take just the intersection with the graph of a function with A, I must be sure this is still a function, right? It might not be the case. If I take the intersection of a function with a subset, I have no idea if this remains a function. But what we just proved here is that they do. They are still functions, right? Yes. Yes.
Why do we know that n satisfies exist x, GA equals to x?
Because this is already an L structure, right? So for sure, this is a good question. So for sure, for every element in my, already, for example, if you're an L structure, you know that, let me put this perhaps here, this in another color. Any structure, you know that this does define a function on n, because n is an L structure. So you know this is an actual function on n, right? So you know that for n, you know that there is for every tuple, let's say d in n to the n, you know that there is some e such that, let me write it here, such that gn of d is equal to e, right? You know this for every tuple d in n up to the n, you know that this is an actual function because exactly d, sorry, there is e, of course. There is e in n, right? Such that this holds. This is because you must interpret every function as every function symbol as an actual function, right? So if this holds for everyone in particular, it holds for this a because a is a subset of n, right? So this has to hold in this structure, right? Just because you are actually an L structure and not just a subset, right? So now we proceed by induction on formulas. So the base step is when phi is an atomic, let's say phi of x is an atomic formula. And this was part of our lemma. We show that any quantifier-free formula is preserved if I have an L embedding. And being a substructure is the fact that the inclusion is an L embedding. So this was our lemma. This is follows from our lemma. From our lemma with part 1, right? In part 1, we already have that we have a substructure, and the lemma says that formulas, atomic formulas were preserved, well, quantifier formulas were preserved with an embedding. So the basic step is just this one. Now the inductive step, let me say it like this, for negation and conjunction, right? This is easy with the induction hypothesis. Okay, this is a direct application of the induction hypothesis to the formulas, let's say psi1 and psi2. You get directly that both the conjunction and the negation are going to be preserved, right? Really a two-line proof. And then it remains the case where we have the existential, and this is exactly where star comes into play again, right? So if now, a phi, let's say x is of the form there exists y such that let's say theta of xy, then we use a star. Right? Let me perhaps erase this instead of erasing. Then we have that A satisfies this formula phi of A. This is if and only if, of course, there is some B in A such that A satisfies phi of B A, right? Here I use the induction hypothesis to have that N has to satisfy, oh, sorry, this is theta. I use the induction hypothesis with theta to know that this is the same as N satisfies this formula. This, of course, implies if there is one B that satisfies this formula, of course, this implies that N satisfies there exists an X theta of X A. You agree? And the reverse is just a star, right? This reverse implication is just a star. If I have someone in, I mean, if this formula is satisfied in N, then there is one in B. This is again for B in A, such that satisfies this formula. And then we just prove the if and only if, and we show the result. So this little criterion is going to be useful in what follows in order to show when two given structures are, one is an elementary substructure of the other. Okay. Sorry for the 5 minutes. Yes.
You say that that's easy. Doesn't also actually follow from the previous lemma?
No, that's a very good question. In the last thing we say that this was true for quantifier-free formulas, right? But in this induction, it could happen that you already have two formulas which have quantifiers, and then you're taking their conjunction. So this step is not just making conjunctions and negations from this one, but it's an inductive step which might involve quantifiers. So we need to redo it, right? But that's a good point. One sometimes thinks that the induction goes like this, but no. I mean, in this point, when we take this psi1 and psi2, these two formulas might already involve quantifiers, but we assume that we already have the result for these two formulas. And then we need to take the result for negation and conjunction. This is why we need to redo it, but it is basically the same two lines that we wrote for the lemma. I mean, it's not going to be too difficult. Okay. Any other question? Let's have a break and we'll get to some examples of this, some more examples of this. So just in case, I hope it was clear when I meant that it was enough to show that A contained the constants and A contained it's closed under functions to understand why this is already enough to show that it is a substructure, right? I mean, there is only one way in which a subset can be a substructure, and is to interpret the relations as the relation intersected the right Cartesian power of this subset, right? There is no other way in which the inclusion can be made in L embedding. So we were forced to show that the intersection of a relation, I mean, we were forced to interpret the relations in this way, and this makes, of course, trivial the condition of preserving the relations for the subset. But for functions, this is not so obvious because we need at least that when I intersect the graph of the function with my set, I need this to be now a function on the set and not that it goes outside of my set, right? But this is exactly being closed under functions, right? And then in this way, we're sure that A is going to be a substructure of the other. I hope this was clear. Okay, now let me show you two theorems. One, I'm going to prove it, and the second one, I'm going to skip the proof for later, which show already that this property that we saw for finite structures does not happen for infinite structures. These are called the Löwenheim-Skolem theorems. So one is the descendant one, and one is the ascendant one. Let me give you first. Let me write both, and then let me prove one of them. This is the theorems of Löwenheim-Skolem. One is the downwards. Let's say this is the downwards version, and it says the following: let n be an L structure. Perhaps I want to take the same notation as in the notes, right? And let S be some subset of n, such that the cardinality of this subset is as follows. It has to be, well, the cardinality, let's say, of S, the cardinality of language, and let's say Aleph 0. Right. Let S be a subset of n, and kappa be a cardinal. Let me put here cardinal, such that it sits in between the cardinality of n. It is bigger than the cardinality of S, bigger than the cardinality of language, and it is an infinite cardinal. Okay. Then there is an elementary substructure n of m, such that m has cardinality exactly kappa, and it contains S. Okay. So you can think of this theorem as saying, for example, something like this. If you have, suppose you have a very, very big structure, let's say, for example, the complex numbers, right? Suppose you have the complex numbers, which is of cardinality 2 to the Aleph 0, right? It has the same cardinality as the real numbers. Now take any subset, which is, for example, of countable size, right? Then this is countable. The language of rings is for sure is finite, so this is countable. So this whole max is just countable. Suppose you take kappa also to be countable, right? Just the cardinality Aleph 0. Then this says that you're going to find an elementary substructure of the complex numbers, which is of countable size, right? So in particular, for example, if you only have proven the fundamental theorem of algebra for the complex numbers, right? The complex numbers are algebraically closed. This is telling you that there is going to be an algebraically closed field which is countable. Okay, for sure you know that the algebraic closure of Q is going to be countable, but this is telling you, for instance, that I don't know, that you have well, this is
use the choice action.
this for sure is going to use at some point some sort of some lemma in between. That's correct. Yes. Well, I'm going to use some at least in some point I'm going to use some cardinal arithmetic, which uses somewhere the axiom of choice. Yes, that's correct. Okay, but this says you can go downwards, right? You can, if you have a very big structure, you're going to find an elementary substructure, even containing any subset that you like. Okay, so right. Okay, let me give you the upward version directly of this theorem. Upwards, it says that let now M be an infinite L structure, and now kappa be a cardinal such that it is bigger than the cardinality of M and the cardinality of my language, and that's it. Right? My cardinal is bigger than these two things. Then there is an elementary extension, right? There is N such that M is an elementary substructure of N, and kappa, N, sorry, has cardinality kappa. So this now says something on the contrary, that you can go up, right? So this says, for example, that you're going to have algebraically closed fields of any cardinality bigger than Aleph 0, right? You give me the cardinal you want, right? Then I can take an algebraically closed field, which is going to be, well, for example, you give me a cardinal, I don't know, kappa, any infinite cardinal, right? Then from the downward version, I know that there is going to be an algebraically closed field, which is of cardinality countable. And now I take, since if my k here was countable, well, I'm done. But if my kappa here is super big, then I know that there is going to be an elementary extension of this countable algebraically closed field of cardinality kappa. And since we know that this being algebraically closed is preserved by this relation, then we're going to have algebraically closed fields of any size, right? This is if you want to, I don't know, if you have read Weil's algebraic geometry, he always worked in some sort of super big algebraically closed field where everything is happening. This is a way to formalize this type of old algebraic geometry, right? If you really want to prove things perhaps about C and you think your ambient algebraically closed field is too small, then you just go to a very, very big algebraically closed field in which everything is happening, and you do algebraic geometry the old way Weil's way. But this is one way in which you can formalize this idea. You're going to have always algebraically closed fields of very large cardinality in which you can kind of embed everything which is happening in your proofs, right? Even if you sometimes go a little bit out of C, doesn't matter. Everything can be embedded somehow in a very, very, very large algebraically closed field. And this is one way in which you can formalize this sort of arguments. Okay, let me prove you the downwards version, and the upwards version I'll skip it for later in the course because we need one more tool that I haven't yet introduced. So let us show proof of the downwards theorem. Okay. So the first remark is that without loss of generality, we may assume the cardinality of S is already kappa, right? Because if S is smaller than kappa, well, just put an S prime which contains kappa elements. And if we prove this from S prime, of course, since S prime is going to contain S, the same holds, right? Because we'll take any S prime containing S such that the cardinality of S prime is kappa, and the proof, and if the result holds for S prime, it holds for S. The result holds for S prime. It also holds for S. Right, so we can already assume S has the right cardinality. And what we're going to do is to construct our model M inductively by defining bigger and bigger sets. So we define sets Si for I in N inductively as follows. So
Sorry, could it be that the cardinality of S is bigger than kappa?
no, we said here kappa has to be smaller than the maximum of all these cardinalities, in particular than the cardinality of S. But if I take it to be really strictly smaller, then what I'm saying here is that, well, I can just take a bigger S and this will do, right? Since N has more or equal than kappa elements, I can for sure find this S prime, which is still a subset of N, right? Okay. So we're going to define these sets inductively as follows. Our S0, we're going to start with our set S. And the idea is that we want to ensure that this star property from Tarski test is going to be satisfied, right? So I start satisfying it for S, right? But then in this process, I might add new elements, right? And then I need to take care of this in the next step. But if we do this omega times, right? If we do this enough times, then we're sure that we're going to satisfy star everywhere. So this is the idea of the inductive step. So for Si plus 1, right, we're going to define it as follows. So let me perhaps say here what I wanted to say. This is perhaps the right thing. So I'm going to define it as some right. I'm going to define it as some set A of phi for phi in a given set, let's say, I think it's AI. And I need to define you what this AI is and what this A phi is. Where? So this AI, I'm just going to list all formulas phi of X, and here I'm going to put some, let's say, A, right? such that, right, perhaps let me call this B phi such that we are not, such to distinguish this A and B. So here I'm going to list all formulas such that phi of xy is an L formula with x just one variable, right? And such that n satisfies the formula there exists an x phi of x a with a in S I, right? So we assume that I already defined SI, right? And the set SI plus 1 is going to be some set that I haven't defined, but I'm defining this set of formulas SI as exactly those formulas for which n thinks that there exists an element x satisfying this formula for elements in SI. And if you think now for the moment for S0, then what I'm thinking is n thinks that there exists an element that satisfies this formula for an element A or a tuple of elements in S. Actually, I should put here to the Y, right? To be precise, this is a tuple. It can be an arbitrary large tuple, right?
So you're reproducing the proof of the construction of algebraic closure.
In a sense, I'm doing this, right?
You know, you are joining more and more roots.
Exactly. I'm joining roots, but exactly. If I have new roots, then these are new coefficients, then I need to do this at least omega times. Exactly. I'm doing exactly this if you want. That's totally correct. Now, which are these elements? Those are the witnesses I have for this formula, right? So let for each formula phi of xa in my set AI, let V phi be an element of n such that n satisfies now this formula phi of B phi A, right? If I am a little bit more precise, I should put here.
And you use axiom of choice.
Exactly. I'm choosing here a representative or a witness for this formula. You're totally right. Let me put here, perhaps this is, I need to put.
All, then you use the cardinal.
Correct. Correct. Exactly. I need exactly just one for each formula. And the fact that the formulas, this set of formulas, we need to do some counting about how big are these sets, right? But the number of formulas and the number of elements of SI, they're always going to be bounded by kappa. And in this way, this procedure will never exceed kappa. That's correct. Right? So for every one of these formulas, I'm taking an element in N, which is a witness, because if there exists one, well, there must exist one which does satisfy this formula. And I'm taking this witness and add it here. Let me put here perhaps a little bit, this is more precise. Phi of XA belongs to my set AI, right? Notice that this is an easy observation is that note, perhaps here, note that this set already contains SI, right? Note that SI is already contained in SI plus 1, because for sure, all these formulas contain also the formula for if, let's say, A is contained in SI, the formula phi, well, the formula X is equal to A, right, belongs to this AI in AI. So since this formula belongs to SI and the only possible witness for this is A, I do have a chain of subsets, right? Now take M to be the union of all SIs, right? Then by the Tarski test, we have that M is an elementary substructure of N, right? This is almost immediate by construction, right? Since we write it, indeed, let now phi of x, y be an L formula, and take A in M to the N such that N satisfies there exists an x phi of x A, right? Then this, right, since A is equal just to A1 up to AN, all of them must appear, well, if they belong to M, this means that they belong to the union. This means that they must have appeared at some point in one of the elements of the union, all of them, right? And there is some K in N such that A1 up to AN already belong to SK, let's say plus 1, no, actually just to SK to the N, right? Because they belong to the union. But now I solve this problem in the case S plus 1, right? This is what SK plus 1, sorry. So since N satisfies this formula phi of, sorry, there exists x phi of XA, then this formula phi of XA belongs to AK, and then we know that B phi A belongs to SK plus 1, and N satisfies this formula, right? But this means that there is an element. This means there is B phi A in M such that N already satisfies the formula. I need to put here AA and then a big A.
Also, the definition of SI plus 1, I think B phi A,
B phi A
X,
here?
or maybe I think it's confusing.
So this is the set of formulas phi XA, right? These are the formulas with potentially elements in SI, right? For which this formula and A replaced by Y, N satisfies that there exists an X such that this formula is true. Yes? This is just a set of formulas where I replaced one of the variables by elements in SI. Some of the variables by elements in SI.
Such that N satisfies it.
Exactly.
What's the definition of SI plus 1?
Right. Then I said, exactly. Then I said here, for every such formula here, since N satisfies this, right? This means that there exists someone in N satisfying this formula. And I took one element in N satisfying such a formula. This element B phi comma A. Here, perhaps I also need to put, sorry, I wrote it wrongly. This is the case. N satisfies this formula with respect to this new element B phi of A. Exactly. I collect all these B phi A in this. Well, I collect all these witnesses for every formula in this set. Right? And then what I said is that since now I want to apply the Tarski test with respect to M and N, right? To show this, right? So the Tarski test was saying that if this is true for N, then I must find a witness of this already in M. This was what Tarski test was saying. That if I want to show that a subset is an elementary substructure of this one, it was enough to show that every time that n satisfies an existential, well, not an existential formula, but a formula starting with an existential quantifier and some elements in M, then I need to find the witness already of this in M. And this is what I'm proving here. I start with some elements in M, right? Because M is this union, then there must be some K where all of them already appear, right? Because M is just the union of all these SIs, right? If an element belongs to the union, it means that it must belong to one of them. And if I have finitely many, then I just take K to be the maximal K in which all of them appear, right? Because this is a chain, correct? So if you have a chain of the SIs, SI is contained in SI plus 1, then there is going to be at least one K in which is going to contain all of these elements. You agree?
I still have to process, but for now it's clear what
Okay.
it is.
Then what I'm using here is that if this is the case, right, then this means that this formula has to appear in this set of formulas for the K, which contains all these elements A1 up to AN. But then I have a witness already in SK plus 1 for this formula. But of course, SK plus 1 is contained in M, and this means that I have a witness in M for this formula, right? And then we're done. Now, it remains to be sure that the cardinality of this M is K, right? Because otherwise we haven't proved anything. So we know already that since S0, which is S, is contained in M, then we know that the cardinality of M is at least kappa, right? Because we said at the beginning of the proof, we may assume that S has cardinality kappa. So since I contained S, well, I am at least of cardinality kappa. We better be sure that we didn't exceed this cardinality, right? So we proved by induction that I shouldn't have deleted this. Si plus 1. This is the B. Let me keep this. So we show by induction that the cardinality of every Si is smaller or equal than kappa. And this is enough, right? Because if you have, this is enough. This is enough since, well, the cardinality of M is equal to the cardinality of this union of SIs, right? For I in the natural numbers. And then this is, of course, smaller or equal than taking, if each of them is smaller than kappa, this is smaller or equal than Aleph 0 times kappa, right? And by infinite cardinal arithmetic, this is just equal to kappa, right? So it suffices to show that each SI is smaller than kappa. So by induction for S0, this is equal to S. This is done because we said S was just kappa, right? And now we need to ensure, assuming that the cardinality of Si is equal to kappa, let us show that the cardinality of Si plus 1 is also kappa, right? Then we need to count how many elements B of this form are there, right? But this is the following counting. So we need to show that formulas of this form, there are at most kappa, right? So how many formulas in my language are there? Exactly. Oh, I deleted, but I said one of the assumptions of the theorem was saying that, exactly, I said that the language S, the language, 0, right? That this was at most kappa. So symbols in my language I have at most kappa. So formulas as well, right? Because formulas are just finitely many symbols of elements in L. So this is also at most kappa. And then formulas applied also with elements of A, I will also have only at most kappa. This follows since the set AI has cardinality at most kappa. Okay? Good. We already proved the downwards Lovingham's column theorem. And the upwards, I'm going to postpone it for later because we need one of the more important theorems in model theory, which is the compactness theorem. We haven't arrived there, but we will. And once we have compactness, to show the upward version is quite easy. Okay, good. Now we're going to enter into kind of real model theory. And for this, I'm going to introduce now actually theories, right? We haven't done so far anything about theories. And now what comes next is, right, I wanted to, well, let me first define theories and then I would mention to you, I said to you yesterday that I wanted to show you why first order and second order were so different, right? What was the point in not allowing quantifying over subsets? Why is this really indeed really more expressible? I'll get to this point today. So notice that these two theorems imply that for infinite structure, it cannot happen, right? Let me make this point. So observation is that if M is an infinite structure, it does not hold that being elementary equivalent implies being isomorphic, right? This cannot be any more the case, right? Because in particular, if M is infinite, we saw that the upwards Lovingham's column theorem is giving us an elementary extension of cardinality much bigger than the cardinality of M, right? These two structures are going to be elementary equivalent, but for sure not isomorphic. They have different cardinality, right? So what was happening for finite structures is for sure not true anymore for infinite structures. We cannot fix by sentences the isomorphism type of an infinite structure, okay? Let me do this. Indeed, by upwards Lovingham's column theorem, there is some n, which is an elementary extension of M with the cardinality of n much bigger than the cardinality of M. Then, of course, this part implies that these two structures satisfy the same sentences.
Even if you combine the two upwards and downwards, you can stay in the same cardinal.
That's right. But what I'm saying is that in this case, I will find two structures which are elementary equivalent, because if this holds, and these two cannot be isomorphic because they cannot be in bijection, right? But they cannot be isomorphic since there is no bijection between them, since there is no bijection between them. What Javier is asking is perhaps the next better possible thing. This is called categoricity. Let me say it. This is a definition that we're going to use. Definition. So this basically what we have said so far is that for finite structures, being elementarily equivalent characterizes completely the isomorphism type of a finite structure. Because we saw actually that even if the language was finite, there is actually one sentence that completely characterizes the isomorphism type. For infinite structures, this is showing that this cannot be the case. Okay? We cannot, two structures that they look the same with respect to sentences, this does not imply that they need to be isomorphic. However, we can perhaps ask for something, the next better thing that could happen. So let's say we say, oh no, first before I'll give you this definition, I need to really introduce you theories. Okay, this is perhaps better. Okay, let me first introduce theories, and I'll give you this definition of categoricity in a second. Okay, so an L theory T is just is a set of L sentences. Okay, this is what we call a theory. It's just a set of L sentences. Okay, let me give you some. Shall I give you some examples, or first define you a bunch of concepts and then give the examples with the concept first? Perhaps this is going to be better. This is going to be a theory. The empty set is a theory, right? Yeah, that's correct. That's correct. We say T is satisfiable. Also, this is the same as consistent if there is I should have said this before, but doesn't matter. I'll put it here. If there is an L structure M such that M, we say M, well, let me write it here, such that M satisfies every sentence in T, such that M satisfies 5 for every 5 in T. In this case, we write this, this like this. M kind of satisfies already T, right? And we say that M is a model of T. Write it like this and say M is a model of T. Now, finally, we have the word model in this course. So models are just the structures that satisfy, models of a theory T are just the structures that satisfy every sentence of T. Okay? Now, finally, let me give you another definition, right? We let mod T to be the class of all models of T. Okay. Final definition, I guess. Given a class, we say a class let's say C of L structures is axiomatizable. Sometimes in the literature, this is also called elementary. If there is a theory, an L theory T, such that this class C is precisely the class of models of T. Okay, so if I gave you just a bunch of L structures, I want to say that this class of L structure is axiomatizable if there are precisely all the models of a given theory T. Okay? So for example, I'm not sure if I asked you also yesterday a question that was that, well, I say it this way, is there, this is not the same, but right. I asked you, for example, if there was one sentence in the language, in the empty language, such that a structure satisfies this sentence if and only if the structure is infinite. I ask you if you could find such a sentence, right? I repeat. The question was, actually I asked it in different languages, but the very first one was, is there a sentence in the language, in the empty language, such that a structure satisfies this sentence if and only if the structure is infinite? Did anyone think about this? I said it's not possible? Damn it. So I already screwed the exercise. It is not possible, but how to prove this? Yes?
I mean, now we can just use the Lowenheim score.
Uh-huh. How?
That's kind of cheating, right?
No, well, if you have a proof with this, let's see how.
I mean, because if we had finitely many sentences,
Mm-hmm.
I mean, oh wait.
So this is just one sentence
I
that
was
does.
wrong because it's either infinite or, I mean, so if it were possible,
Yes.
actually maybe it wouldn't contradict because we would just be able to get many other infinites.
That's correct. In Lovingham's calling just will give you
Okay.
bigger infinite structures, but still infinite. This I leave it still as an exercise. Perhaps we don't have yet the right tools to answer it, but it would be nice if someone comes with an idea. This is always nice to ask difficult questions, even if at the beginning, perhaps someone comes with a new idea. Who knows? Okay, but it's easy to show now that, for example, the collection of all infinite structure is at least axiomatizable. Now, not just by one sentence, but at least with a theory. Let me, for example, let C be the collection of all, let's say, L empty structures, right? Then, sorry, all empty structures which are infinite. Let me call this C infinite, right? Then this class is axiomatizable. This is, when you see it, you will see this is a triviality, but it's important to know, now that I spoiled the exercise, it's important to see that what I'm saying is that there is no formula such that in a given structure, L empty structure, if this formula holds, then the structure is infinite. This is not going to happen. We'll see later why. But this class does, I mean, is axiomatizable. I can find a whole theory which axiomatizes this. Any idea how we do this? I did it already, exactly, right? It's just writing the sentence, I have more than 2 elements, I have more than 3 elements, but now since I need to satisfy all of the axioms, I mean all of the elements of T, I must be infinite, right? So take T to be the following theorem. I have this formula right? This formula for every n in here. Right? This is the theory. The theory says I have at least n elements, but for every n. So if a model, if a structure satisfies all of them, it must be infinite, right? And any infinite structure is going to satisfy all these formulas, right? However, so I mean, this is one of the difference between satisfying a whole theory and just satisfying one sentence, right? The exercise that we haven't solved is to show that there is no sentences that no single sentence that is going to do this job, the same job, right? What we're saying is that this class is not axiomatizable by a finite number of formulas. We actually need infinitely many, okay? Good. So now we're approaching a little bit more what we do usually in mathematics. Let me give you some theories that you, of course, you're familiar with. Well, for example, what we call the theory of groups. This is also why we call these things theories, right? The theory of groups is just let me call it the theory of groups.
The only symbol that you have in the empty language is the equality.
Exactly. I'm
And
only.
if you write one sentence.
Yes.
You have finitely many variables.
I agree.
And now suppose you have a model.
Yes.
That satisfies the sentence.
Yes.
So
how can it say it's infinite?
Then
yes.
You must locate a subset that is finite and still satisfies.
Right, but it might have quantifiers which are for all, right? Not every formula it's starting with existential. Perhaps you have a more complicated one with for all. Perhaps one way is a little bit more the type of formulas that you will end up. We will see another way, perhaps today. We have plenty of time in this course. Please tell me if you're getting tired at some point. I mean, as a teacher, I don't see it, but I'm sure if I'm learning this for the first time, I will be, well, at some point I will be not putting that much attention and trying to understand. So please say when we should take also a break, or you need some time to understand one of these concepts. I will totally understand.
But for all does not exist. Every formula is, you go by induction, every formula at the end of the day is.
That's true, but you have negation.
Yeah.
So the for all is there. It's just that we don't. Perhaps you need to prove something by induction of formulas. This might be interesting. Yes, that could be a way. But you need to work a little bit. We'll see a shorter version for this, but this could be with a bit of effort. Perhaps this could work. Yes. Yes. Yes, with a bit of effort. I'll think about it to see if this way can work. At least in this case, we're going to see a method which is a little bit more general, and then we'll apply it not only to this case, but to other languages, right? I asked you, for example, if the same was true, but in the language of groups, and then the formulas become a little bit more complicated, right? So the method I will present later will apply also to this one, but in this one, to really go over all the possible formulas, it's going to be much more hard. Yeah. Okay, so for example, the theory of groups in the language LG, well, this is just equal to the axioms you know for groups, right? This is saying that for every x, for every y, for every z, our operation is associative, right? We say that for every x, 1 times x equals x times 1 equals x, right? We need to say this is a conjunction, right? Or our theory might just contain these actions, right? Doesn't matter if we put, in this case, there are finitely many, so I might put just one action with conjunctions or just divide them into several sentences. And I need to say that for every x, x times minus 1 of x is equal to 1. I think, am I missing an axiom of the theory of groups? I think that's everything, right? That's actually a group. So this means that any, now, well, the claim, this is just an observation, remark that, note that the models, I mean, this is of course a triviality what I'm saying, but note that the models of this theory is the class of groups. It's just the class of all groups, right? Now it doesn't matter how you interpret the symbols in this structure. If they satisfy this, they must be a group. And now this is what Nero was perhaps asking. Now this class is really the class of groups with the this can be seen as a category of groups. In this case, the arrows are just embedding us of groups. This is one way in which you can really restrict to this class, right? It's just taking the models of this basic theory, right? Now you can make theories, of course, of rings, of fields, and what we just said at the beginning of this lecture is that we can even make a theory of algebraically closed fields, right? We actually wrote those sentences, right? But this is actually the theory of algebraically closed fields. We say this is called so the theory of algebraically closed fields is called ACF, and this has this sentence, one sentence for what we say these fields, right? Together with all the sentences, let me put it like this, union, all these sentences psi d that we discussed previously, right? Recall this sentence psi d was just saying that every monic polynomial of degree d has a root, right? Something saying that y0 up to yv minus 1, there exists some x such that this polynomial is 0, right? Okay. Perhaps shall I put some, okay. So this is actually the theory of algebraically closed fields. And what we just said is that any field satisfying these axioms has to be actually algebraically closed, right? So we're saying that the collection of algebraically closed fields is axiomatizable. We're having exactly the axioms of this. Now, we can also say perhaps something about the characteristic, right? How can I, for example, just take fields of characteristic of a fixed characteristic? Is this axiomatizable? How? For example, if I take, well, let me say the theory. Oh, of course, this is an L theory. I should say this is a theory in the language of rings, right? I'm taking the language of rings as the basic language for expressing this theory. The L-ring theory of fields, let's say of characteristic P for P a prime number. What should it be? This should be, let's say, fields of characteristic P. What should be this theory? Of course, it has to contain this formula that says that I'm a field, right? And what else?
You just need to ask for, I mean, you're in the language of fields.
Absolutely.
1 plus 1 plus 1.
Exactly. I just do 1 plus 1 plus 1 plus 1 P times, and I take it to be equal 0, right? That was easy. Now, what about fields of characteristic 0? For sure, I need to be a field, so I put my formula of being a field. But how do I make it now?
It's prime. So
It's prime, it's prime, it's prime.
so it's the same, not P, right?
Exactly, but now for every P, right? So I just, here I don't need just, notice that this theory is a finite theory. It actually has two formulas, or I could put the conjunction. Here I need infinitely many, right? Here I need to put not, I put 1 plus 1 is different than P, but this I need to do for every prime, P prime. Oh, sorry. Right, and this is P time.
I was going to ask if there is a way of putting that with finally many ones, but there is only finally many. Okay.
That's a good question. That's a very good question. This is a question about, is a theory finitely axiomatizable, right? This is a theory, this is similar to the question that we were saying here. Is there a way in which I can present this with only finitely many axioms? It's a nice question. We're going to get to that. It could be possible, right? It could be possible that there is a interesting, complicated formula ensuring that if I satisfy this formula, I must have characteristic 0, right? Some strange property of fields of characteristic 0 that implies all of these sentences. We're going to see that this is not the case.
The universal quantifier, if you reduce the universe, the formula is satisfied if you do this field.
That's correct. A universal formula remains true. I mean, goes down, but it has to be a universal formula. So meaning you only have universal quantifiers and then a formula that has no more quantifiers. See, these formulas goes down. That's correct.
And if I have 1 plus 1 plus 1 plus 1 equals to 0,
Yes.
it is okay?
Well, in this case, this is just one formula, and well, this is a little bit of field theory, but if 1 plus 1 plus 1 equals to 0, then you must have characteristic P. You cannot have characteristic less or more. Yes?
If I say that 4 equals to 0, this is okay?
No, because I'm saying here, but if you're a field, you cannot have a characteristic 4, right? This is perhaps also included. Here I can put n also instead of P prime. Of course, I can put just any number, but it is enough to put it for primes, right? But the theory is going to be the same. I mean, the models are going to be the same if I put here only for primes or for any natural number, right? Because if I'm a field, the characteristic can only be a prime number or 0, right? I cannot have characteristic 4. That's impossible. Yes. I haven't answered any of these questions about finite axiomatizability, right? Notice that the question that I asked you about, is there one single sentence that is true in a L-empty structure if and only if the structure is finite? It is the same question as saying, is this theory finitely axiomatizable, right? Because I can take the conjunction of these finitely many formulas, and this is going to be just one formula that axiomatizes this theory, right? So this is the same kind of the same flavor question. If this theory can be finitely axiomatizable, then I'm going to find one single sentence that captures the fact of being infinite, and I'm saying this is not the case. And this is also not going to be the case in this one here. Okay. You can have right. I want to, perhaps this is a good point where I can give you this example. I don't recall by heart all the actions, so this is yes.
So you write the formula in the prenex set.
Yes.
And
In the prenex form, then I need existent for all. Because
yeah,
right? Because yeah, every formula is equivalent to one in prenex form, but there I really need for all and there exists because I use negations to put everything, all conjunctions and negations to one side. So you have an alternation of quantifiers which might be.
Suppose that the formula is satisfiable. So you have n variables.
Yes.
And let's divide the variables in two types: those that have existence and those that have for all. And because the formula is satisfiable, I can substitute the existence variables by elements.
That's correct, but depends on the order, right? I mean, if you have for every x there exists y, you cannot just directly take some y because this y is going to depend on x. So, right, if I have a formula of this form, right, phi of x, y, this is definitely not the same as there exists y such that for all x. These two formulas are not the same, so you cannot directly take all the existentials. This there exists will depend on the x that you choose first. Right?
Here exists an example. I can say elements such that the formula is satisfied.
But for example, this is a sentence, right? Suppose
that this is
exactly. Suppose that this is true in some model M, right? And perhaps this is a quantifier-free formula, right?
Yeah.
How do you proceed?
So for any given value a for x, there exists
Y such that something. B, exactly.
Okay, so yeah, so now it gets
A little bit, yes. Yeah. But I think it's not a bad approach. I mean, perhaps with, and of course you need to treat this for any possible alternation of quantifiers. This might get a little bit complicated. Okay, what I wanted to tell you is
from sets to sets. So you take the universal variables, you give values. This is a set, and it gives a map to another set. That is also fine.
This is basically what for all exists is saying, right? But then if you have a for all exists for all, this is saying that you have a map such that something happens. This starts to be, and it can have a very long alternation of quantifiers, right? That's correct.
There are ideas in the basis of theories which are only infinite models.
That's true. That's true. I asked you
Something about you will have to use the structure of the formula and the language.
I see. So this means that this approach is blocked.
Well, this approach.
No, but it exists. There are finite set of formula which has infinite models.
But
Yes, I asked.
This idea that I'm proposing should be blocked.
For equality, not for equality, perhaps not for just for not for the empty language, perhaps not, but in general, yes.
Sorry for interrupting.
No. It's good. It's good to think about these problems. Right. If I give this example, I spoil a little bit this fact. So, right. I just continue. Right. Okay. Let me let me give you the usual piano arithmetic in first order, right? This is just the idea of trying to axiomatize the natural numbers with first order axioms, right? So this, I think, is the following. So the language of piano arithmetic is the following. I don't know them by heart, so I better put them all. This is a unary symbol, function symbol for successor, addition times, and the 0. Okay, so S is unary. Of course, plus is also the same as times are binary functions, and this is a constant symbol. Okay, the axioms are the following. One, this is 0 is not the successor of anyone, right? For every x, for every y, the successor function is an injective function. We say that for every x, x plus the successor of y, sorry, for every x, for every y, x plus the successor of y is the same as the successor of x plus y. This is basically saying how the successor and these two functions work. Also, for every x, we have that x times 0 is 0. And finally, this is n2, n3, n4, and 5. Oh, I missed one. Right, sorry. N5 is for every x. X plus 0, of course, is still x. And N6 tells me how the successor works with the times. So for every x and for every y, x times s of y is equal to x times y plus x. Okay. So those are finitely many axioms, and now I need to give you induction, right? The idea of the natural numbers is that they satisfy induction, right? But usually, how do you phrase induction? Usually, induction is phrased for every subset, right? This is bad. I cannot say anything about for every subset. So this is a scheme that I'm going to have for every formula. So this is a scheme that says something like this. This is N7, but for every formula phi. And I explain you what this means. So this says for every y, if phi, so suppose that I have here a formula phi of xy with x1 variable. And this is an L formula for this language, okay? Right? Suppose that I have this formula. Then what I'm going to state in the axiom is whatever natural number y is, induction is going to hold for the formula. So if 0 holds for this formula, if this formula holds for 0, and for every x, it does hold that phi of xy implies phi of x, sorry, the successor of s of x holds, right? Sorry, I put this here again. So if these two things hold, right, that 0 is satisfied in this formula, and that if x is satisfied, then the successor is satisfied, right? Then the formula holds for every x. Right? You see what I'm doing? I'm just kind of instantiating the induction just for the formula. And here, phi is any L formula phi of xy. Y can be a multivariable, right? But x has to be of length 1, right? So piano arithmetic for first order logic, it cannot quantify over all subsets of the natural numbers, but just on the subsets that I can define by formulas, right? So this is much weaker than piano arithmetic, the usual one. The usual one is that the one we know for second order, which is basically these axioms. So let me write it here. This is second order piano arithmetic, right? This is, let's say, just piano arithmetic first order. Second order, it has n1 up to n7 plus an axiom saying really for every subset A of the natural numbers, if 0 contains A, and of course it holds that for every x is in A implies x, the successor of x is in A, then these two things imply that A is equal to n. I mean, that for every x belongs to A, right? This is a much stronger axiom because here I'm quantifying over all possible subsets of the natural numbers. And here actually I have such a statement only for actually countably many subsets of the natural numbers. Because, well, formulas, there are only countably many. Possibilities for this y to be a natural number, there are countably many. So at the end, in this theory, I'm only saying that induction is valid only for countably many subsets of the natural numbers. But subsets of the natural numbers, there are 2 to the aleph 0. So this is saying something much weaker than this axiom, okay? And in particular, let me tell you something. And here we're going to see really that this is much more stronger. This is an exercise. Show that if any other n satisfies piano arithmetic, let me call this piano arithmetic 2, let me call this n, then n has to be isomorphic to the actual natural numbers. Okay? If you satisfy these strong axioms in order 2, then actually the unique structure that satisfies this structure up to isomorphism is really the natural number. So we can say those axioms really capture completely the natural numbers, right? However, this cannot hold here. Why? This for sure cannot hold here. Any guess why? I mean, it seems.
I guess you could do the same thing in a bigger set that contains the naturals.
Why and why? I mean, we have one theorem that says this, but which one? Exactly. We can apply Löwenheim-Skolem to get a model of this theory, which is of cardinality 2 to the aleph 0, right? So what we said is that no theory of first order logic can capture up to isomorphism infinite structures. And in second order, it does happen. We can capture exactly the natural numbers with these axioms, right? But in first order logic, this is never going to be possible. We can have models of piano arithmetic which are of cardinality, the cardinality of the reals. And they do satisfy exactly all these axioms. This is a consequence of Löwenheim-Skolem. So second order logic is much more expressible. It is really saying much more. It's fixing me the isomorphism types, for example, of the natural numbers. But this we cannot do with first order logic. Okay. Nevertheless, we're going to see that first order logic has very nice properties that we want to keep and pay a little bit the price of not being as expressive as second order logic. Okay.
So a model satisfying those axioms could have like crazy properties of numbers.
I mean, it cannot have crazy properties because it will behave similar to the natural numbers, right? You can still do induction. It's just that, for example, it's going to have perhaps elements which are bigger than any natural number, right? And you still need to prove in the induction step something like this for these new numbers in your structure. But it behaves very similar as the natural numbers. You have induction. It's just that you need to show this part is not of the form, well, it's not n plus 1, but now some x in your structure, which might be some strange number, right? But if you prove this, then you prove that this is true for every element in your structure, for example. So they do behave a little bit like the natural numbers, but they are really big structures, right? Yes.
I have one question, just in case you already solved an exercise. So, can you write a finite structure satisfying n1 and 6?
That's a good question. So you want just a finite structure satisfying n1 to x6?
This is a finite sentence.
This is a finite sentence, right? And you want now a finite structure satisfying it.
I want to know if this exists. So because intuitively you take the successor of successor, so can be the 7th iterate of the successor equal to?
That's a good question. It doesn't seem to, right? Because if you're finite, being injective implies being surjective in particular, right? So 0 needs to have an element. So that's already not possible. Well, if I have a function for successor, right? The question was for groups. At least for one language. That's good. That's good. I agree. I totally agree. Let's write it because I like it. That's correct, but that's the proof. Let me write it because I think it's a nice example. So consider even easier, right? Consider the language L, which has one unary function symbol and a constant, right? So the arity of this symbol is 1 and 0 is a constant of L, right? And consider the two axioms, consider the theory. Doesn't matter, consider the formula actually. The formula, sorry, the sentence. L sentence. For every x, for every y, Sx equal Sy implies x equals y, and for every x, S of x is different than 0, right? Let us show that M satisfies phi, right? If and only if I think, right, if, well, that's true. That's true. That's true. That's correct. That's correct. I can have even infinite structures which do not satisfy this sentence, right? But at least we have one direction, right? So that if M satisfies this, then M is infinite. At least this is correct, right? And well, the reason was what we just said. If we prove the contrapositive, if this is finite, if I am injective, I am surjective, right? But then here I'm saying that I'm not surjective, so this gives me a contradiction. You're right. Well, give me 1 second. Maybe perhaps we can. Right. I agree. I could have said there exists an element X such that it's not in the image, right? I don't need the constant. I agree. Okay. Okay, good.
By the way,
Yes.
The ordinals.
Yes.
I do agree with this action. Yes, it's a model. The set of ordinals. Well, the set
You need to be careful with the way you define plus and times for ordinals, because ordinal arithmetic it agrees in the natural, but then it gets a little bit different, right? For example, yes. Yeah, I need to be careful with. For example, ordinal arithmetic is not the addition is not commutative, for example. So this is not going to be a model, right? Ordinal arithmetic is not true that omega plus 1 is not the same as 1 plus omega, right? Okay. Now I think we're entering this theorem that I told you that was going to be one of the main theorems of model theory, which was this compactness theorem. Oh, wait. Even before this, I wanted to. Oh yes, there are plenty of things before doing this. So perhaps compactness is going to come tomorrow. Now, let me give you some more definitions. Definition, given an L theory T and an L sentence phi, we write that T kind of entails or implies phi, or phi is a logical consequence of T for the following implication. If M is a model of T, then M has also to be a model of phi. Okay? So this only means, I mean, I know that this symbol was used for models, right? But now I'm using it between a theory and a formula. And this also only means that any model of the theory must be also a model of the formula. Okay? Right? So this is kind of a logical implication from T. That I cannot have a model of T which satisfies the negation, for example. Okay? Now we say a theory, an L theory, is complete if for every L sentence phi, either phi is a consequence of T or the negation of phi is a consequence of T. Okay? So basically we're saying this T decides for every possible L sentence. Either phi is an implication or its negation is going to be an implication. And in this case, we say that T is complete. Okay? Let us see. I mean, it's kind of difficult to get really complete theories, but there is one example which is very easy. Examples. Given an L structure M, this set, which we call the theory of M, this is the set of all sentences phi such that phi is a sentence and M satisfies this sentence, right? Then of course this is a complete theory because For a model, we say either I satisfy a sentence or I don't satisfy it, right? Then, of course, this makes this true. Is a complete L theory, right? Because if you give me a formula, either the model satisfies a sentence, either the model satisfies this sentence or not. And then the formula or its negation is going to be in the theory. This is the most basic example of a complete theory. It's just all sentences which are true in a given structure, right?
In the definition, this is here, there is always already a model. Wait, what's this called? M?
So in this,
it's already hidden in the definition of theory. L theory. Is it true?
no.
No.
A theory is just a collection of formulas, right? A set of sentences, sorry.
And for the definition of sentences, there's also no
No structure, no M anywhere.
M is called structure. Yes?
Exactly.
But here, in this first definition, this must be true for some specific structure or for all structure?
For every. This is for every M. Let me put it here. For every L structure M, it must hold this implication.
The second one also is for every L structure.
Here, there is here, I don't need any L structure, right? Because what I'm saying is that I fixed one sentence and either this or this must hold, right? Yes? Then if I take T to be this set, which I'm defining as the theory of M, then this T has to be complete, right? Because, let me perhaps write it. Indeed, given phi and L sentence, well, either, let me put it like this. One of the following happens, right? One of the following happens. Either M satisfies this sentence, right? Or M does not satisfy the sentence, right? I have only these two choices because it is a sentence. A sentence is either satisfied or it's not satisfied, right? This implies, of course, that phi is in T, and this implies that M satisfies the negation by definition of the negation, and then implies that the negation of phi is in T. So since one of these two happens, either one of these must happen, which is the definition of being complete, right? Notice that if a formula, well, perhaps let me do the last implication. This, of course, implies that this holds, right? Because if phi is a formula in T, then this implication has to happen, right? Trivially, right? Because if I am a model of T, in particular, I have to be a model of phi if phi is an element of T, right? So this, of course, happens also here. The negation of phi, sorry, T implies the negation of phi, right?
Okay, so actually here it works already for any other model, any other structure.
For any structure, exactly. Well, no, I'm taking M because T was defined to be the theory of M, right?
Yes, so you start with one structure and you define it like this, then you get a conclusion that is applied to any structure.
That's correct. That's correct. I mean, if I want to show this, I need to show it for any structure. But since the formula is already in T, well, this is trivial, right? Because if any structure satisfies T, by definition, satisfying T means that I must satisfy every sentence. And since this sentence is in T, well, I must satisfy this sentence in particular. Yes? Okay. Now, okay, this was an example, a very trivial example of a given theory, but in this case, I didn't give you kind of axioms. I just give you all the formulas directly, right? So for example, is the theory of groups complete? We can ask this. Does the theory of groups, Ilya is laughing.
So you can prove Gödel incompleteness by constructing two models.
Exactly. We should construct a model that satisfies T and does not satisfy a given sentence, and another model that satisfies T and satisfies the negation, right? So we need two models of TG, so two groups.
Is this the way Gödel proved the theory?
I mean, to prove at least, not yet. But there, I mean, let's answer this question first. Is this theory complete? By any means. Why?
I mean, if it were complete, all groups would be isomorphic.
Not true. That's not true.
But I mean, you can define a segment like a billion, for instance.
Right. Exactly. That's good. No, since, for example, the formula phi saying that my group is a billion, right, is a formula that is satisfying some groups, but in others is not, right? So since this formula, it does not hold, okay, since for this formula we have that T does not imply the formula, and T also does not imply its negation, right? Because to show this, we need to show a group which is not a billion, right? And to show this, we need to show a group which is a billion. But of course, we're going to find both, right? Since there are groups, so EA models of T, so of TG, sorry, which are a billion, and also groups which are not. Okay, well, let me then extend. Let me take now the theory of groups, of a billion groups. This is just the theory of groups together with this new formula phi. I added to my axioms. Is this now a complete theory? Still no. Any way to show that this is not complete? It should be. Sorry?
Cardinality.
But cardinality can, okay, that's correct. I can show that there are finite abelian groups and infinite abelian groups. I agree. But okay, let's take out this issue about infinite and finite, because we say that for finite abelian groups, we know that there is one formula completely, I mean, given a finite structure, right, we can completely describe its type. So perhaps let me say already infinite ones. So I want to say infinite abelian groups, right? The theory of infinite abelian groups. This is going to be the theory of groups. I say I am abelian, and I say these formulas that I have infinitely many elements, right? I put all these formulas, exists one, exists xn, such that they're all different. Good. Sorry? Torsion free. This is not complete anymore. Not yet. So I have infinite abelian groups which have torsion and others which have no torsion, right? So this is not complete, not yet complete. Right, since there are infinite abelian groups with torsion and without. And torsion can be expressed, right? Let's perhaps be a little bit more precise with this and express torsion. Torsion and without, right? Let's see that we can say, well, at least have being of torsion a given number, right? I can say that I have elements of a given order, right? This I can say, right? I can say how exactly. Let's say let's define this as theta of order n, right? Then this is something saying like there exists x such that x to the n, where this is just x times x times x. This is equal to 1, right? This is all right. Thanks. And x is different to 1. Thanks. Otherwise, I'm of course saying a triviality. Cheers. Right? And of course, there are going to be groups in which this is true, and there are going to be infinite and abelian. And how do I say, for example, how do I capture the theory of what should be the theory of infinite abelian groups, which are torsion-free? Sorry for this horrible description of my theory. So this has the theory of groups. Let's put also the formula phi code for abelian. We can add again all these formulas, but actually since now I am going to be torsion-free, this already subsumes to be infinite, right? If I am torsion-free, then I think I'm going to be infinite already directly. So how do I say that I'm torsion-free? Of the negations, right? So I put, if this is the theta n, then I need to put not theta n for every n in the natural numbers, right? And these are torsion-free, right? Yes?
Sorry, but I'm still thinking of the first example.
Sure.
So the thing is, so couldn't there be moral structures? I guess there are moral structures satisfying
Absolutely.
models of that theory.
Absolutely. Actually, the Lovingham's-Collins theorem tells you this, right? If M is infinite, right, there is going to be models of this theory of any cardinality.
However, you only proved.
No. Go. It's good.
You only proved it by using M.
Yes, because know that I only need to show. I only need to show.
Is this last implication because phi is contingent implied by it. So that last application already involves all n, right?
Correct. I mean, let's do this slowly because I don't want anyone to be missed. So we need to show that given, I mean, what we want to show is that given an L sentence, right? Phi, right? We need to show that the theory of M, which this is T, right? This is my T, that this implies this phi, or the theory of M implies its negation, right? Now, I need to show this disjunction, right? I mean this or. So let me do it in another way. It is basically the same, but let me do it in another way. So suppose one of these does not hold, right? Suppose suppose the theory of M does not imply phi, right? And I want to show that then it has to imply the negation, right? What does this mean, right? This means that there is some model N of this theory, right? Some model such that N does not model this formula phi. You agree? This is just the definition, right? Now, if N is a model of this, then N satisfies every formula phi, every sentence phi for phi in this theory, right? Because this is what this means. I need to satisfy every sentence for every sentence in this set, right? But notice that the sentences in this set were defined like this, right? So this means that this is if and only if M satisfies phi by definition of this theory, right? Exactly. So this implies M does not satisfy phi, and this implies M satisfies the negation, right? If I don't satisfy this formula, I need to satisfy the negation. But this implies that the negation is an element of the theory of M, right? And then, well, this is exactly what implies here, because if I am an element, for sure, this implies that the theory of M implies this formula, right? This is another way of showing it, but basically this is telling you that you can already take M here to decide if the formula is going to be in T or not. Yes? Perhaps this way clarifies a little bit the proof.
Then how can we use the mechanism in the example one in the group sense of group?
Well,
for example, you start with model that is
yes, you can take a group, yes, any group. And if I take now its theory, the theory of a given group G, well, this is all formulas in the sentences in the language of groups, which are true for a particular group G, right? That's what it is. But I have no axioms for this theorem. I mean, in this case, every such formula is inside already my set T, right? In the examples I'm giving you here, without fixing a group, I am giving you just a small collection of sentences and hope that this small collection of sentences already is complete. So it's determining all other possible sentences of the language of groups, right?
So in this, if you use the mechanism from first example, later on you get a complete
LG theory, correct, for this one, right?
This actually essentially will be just fix this group already, or what do you think?
Not necessarily. If the group G is finite, yes, because this is the exercise I gave you, that if the group is finite, basically this already contains the formula determining the isomorphism type of the group. But if the group is infinite, then it does not, because by the upwards Lovingham's column theorem, this theory is going to have models which are of cardinality whatever you want, right? So it cannot fix the isomorphism type of G. You're going to find models of this theory which are bigger than G itself.
Therefore, it can classify any input new group if it's there or not.
It only decides sentences of groups. This does not imply that it decides the isomorphism type, right? So a model of this theory is going to be very simple from the classes of sentences to G. So you cannot distinguish them apart with sentences. They're going to satisfy exactly the same sentences. But this does not mean that they are isomorphic, right?
Okay, well, this fix. Oh, okay.
Right. Exactly, only sentences. Only sentences. So what about this theory now? So we have a billion groups which are torsion free. No. I want to see if this is complete or not.
Yeah, no, I'm saying that it's not.
Ah, that's a very good question. Do you think there is a sentence for being finitely generated?
Well, not a sentence, but a set of sentences.
A sentence. That's a very good question. Which would be that?
So if it's when you have to run for each. So if it's generated by one element.
Yes. Okay.
For every y exists. No.
Why exists an X.
No, but this is very good. Let's do this example till the end because it's a good trial. You can say it is generated by one element. You can say it is generated. Exactly. Look, this is good. You can say it is generated by one element, right? You're saying there exists some X, right? Such that for every Y, and now we're in LG, and now you need integers, but you need like a disjunction, but infinite disjunction, right? You need to say perhaps this Y is going to be, I don't know, well, X times X minus 1. What do you want to say? I mean, right? Exactly. You want to say something like this. But this is just that every element is going to be generated by products of n. But this is much stronger than being finitely generated, right? Yeah, that was a good trial. So no, we cannot say, well, this is not a proof, right? We just didn't succeed to say it. But well, perhaps this is at least.
You cannot say there exists an n.
You cannot say there exists an n. That's correct.
And
That's correct. But then notice that for a fixed n, your axiom is already saying something too strong, right? Already the axiom of 2 will say that every element is the product of x and x, right? But you need to say then that you're free, right? Then.
Okay, so I was thinking like you just take like z to the n and just start making your map to the n.
Right. This. Yes.
I think it's possible because once we cross the national order, the second order logic is involved.
To some extent, you're right. We will try to make precise your account. I mean, we won't be able to say finitely generated in the language of groups, unfortunately. But so far, we only have just we don't have a formal proof to say this is not possible to be expressed. But we just saw that this seems to be difficult to be expressed, right? At least not from the obvious attempts. But we still don't know if this is complete or not, right? Let's leave it for today with the question if this is complete or not, and we will see an answer tomorrow, perhaps with a theorem related to this. Okay, today we really did the full 2 hours. I think the second exercise set is already in the webpage or will be in the webpage, and there are a couple of exercises there which are a little bit more difficult than the rest. Some of you are group theorists, right? No? There is a nice exercise for the group theorists there, is to show this one. That if you have 2 groups, G and H, in the language of groups, right? If this group here is simple, show that G must be simple too. It's a funny exercise because we will show later perhaps that being simple is not expressible in first order. Nevertheless, you're able to put it down if this is an elementary substructure, right? Nice exercise if you want to think it for the people interested in groups.